You already know that the scalar or dot product of two vectors A and B with angle theta between them is equal to the product of the magnitudes of vectors A and B and the cosine of angle theta. Now, let us observe an interesting property of dot product of vectors. Consider three vectors A, B, and C. The dot product of vector A with the sum of vector B and vector C is equal to the dot product of vector A and vector B plus dot product of vector A and vector C. This property is called the distributive property of dot product over vector addition. Now, let us learn about the multiplication of the dot product of vectors with a scalar. The dot product of vectors A and B multiplied by a scalar lambda is equal to the dot product of lambda times vector A and vector B. It is also equal to the dot product of vector A and lambda times vector B. The distributive property of dot product helps us find the dot product of two vectors given in their component form. Consider two vectors A and B. To find the dot product of vectors A and B, we multiply their component forms. We know that dot product is distributive. Using the distributive property, we can expand the dot product as shown here. We know that unit vectors I, j, and k are mutually perpendicular to each other. We also know that the dot product of two mutually perpendicular vectors is 0, and the dot product of a unit vector with itself is equal to 1. Substitute the corresponding values in the expansion. Thus, we find that the dot product of vectors A and B is equal to A1b1 plus A2b2 plus A3b3, where A1, A2, and A3 are the scalar components of vector A, and B1, B2, and B3 are the scalar components of vector B. Consider a directed line L and vector OA represented as vector A, making an angle theta with line L in the anti-clockwise direction. We will find the projection of vector A on line L. Drop a perpendicular AB from point A to line L. Now, vector OB, represented as vector P, is the projection vector of vector A on line L. In right-angled triangle OBA, cos theta is equal to OB upon OA. Thus, vector OB or vector P is equal to vector A multiplied by cos theta. The magnitude of vector P is called the projection of vector A on line L and is equal to magnitude of vector A multiplied by cos theta. The direction of projection vector P depends on the angle theta that vector A makes with line L. This leads to some interesting observations. If theta is equal to 0, then vector A lies along line L and projection vector P is the same as vector A, and has the same direction as line L. When angle theta lies between 0 and 90 degrees, projection vector P points in the same direction as line L. If theta is equal to 90 degrees, vector A is perpendicular to line L, and its projection vector P is a zero vector. When theta lies between 90 degrees and 180 degrees, cos theta is negative, and hence the direction of projection vector P is opposite to the direction of line L. If theta is equal to 180 degrees, then vector A lies along line L. In this case, its projection vector P is equal to negative vector A, and its direction is opposite to that of line L. When angle theta lies between 180 degrees and 270 degrees, the direction of projection vector P is opposite to the direction of line L. If theta is equal to 270 degrees, vector A becomes perpendicular to line L again, and its projection vector P becomes a zero vector. When angle theta lies between 270 degrees and 360 degrees, the direction of projection vector P is the same as the direction of line L. Projection vector P of vector A is also equal to the dot product of vector A and unit vector P along line L. Let us replace line L with another vector B and find the projection of vector A on vector B. The projection vector of vector A on vector B is equal to the dot product of vector A and unit vector along vector B. The projection vector of vector A along vector B is also given by the dot product of vectors A and B divided by the magnitude of vector B. Let us look at the component form of vector A again. The scalar components A1, A2, and A3 of the given vector A are the projections of vector A on the x, y, and z axis respectively. You can also determine the direction cosines of a vector from its component form as shown here. Direction cosines can also be used to express a vector in its component form. A unit vector can be represented using its direction cosines as shown here.